Hi, welcome to Math 2LA3. My name is Craig and I'm the instructor for this course. In this short introductory video, I'll give an overview of the course outline, and I'll go over some motivation and context for what we'll be learning in this course. Okay, so all the important course information and announcements is on Avenue to Learn. So if you're watching this, I'm assuming you've already found this. So the main way the course will be delivered is through in-person lectures, which will be in ABB 102 on Thursdays and Tuesdays starting at 7. Okay. The first meeting date will be on June 21st. So I will post lecture notes for the lectures afterwards, but I highly recommend you attend all the lectures that you can, because I'll say a lot more than is on the screen, and I'll give some direction and advice for studying for the tests. Okay. And also there'll be some short pre-recorded videos like this one. Okay. Just adding extra examples or clarifying important concepts. Okay. So as far as our evaluation goes, there's going to be 2 in-person tests, 1 in-person exam, and 7 assignments. Really 6 assignments, but we'll count it as 7 here. So the assignments will be distributed and submitted and graded on CrowdMark. So you already should have gotten an email inviting you to submit the first assignment on CrowdMark. If you haven't gotten that already, send me an email and I'll sign you up. Okay, so here's the 2 grading options we have available. Okay, I will automatically choose the higher of these 2. Okay, so with the second option, we're just going to take the best of the 2 tests that you write. Okay, the first option, as you can see, will count them both. Okay. So if you MSAF one of the assignments, then the weighting will go to the final exam. So displayed here are the important evaluation dates for the assignments and the tests and the final exam. So the first assignment, assignment 0, is already accessible on CrowdMark now. Okay. There's no mathematical content on this assignment. It's just to make sure you can use CrowdMark. Okay. It is worth 1% of your grade, so please complete that. Okay. Assignments 1 through 6 are the sort of real assignments, okay? And they're due on the dates listed here. Okay? And you'll submit those on CrowdMark. So test 1 will be on Tuesday, July 5th. Okay? All of the tests and exams take place during the lecture time booked for that day. Okay? So on Tuesday, July 5th, starting at 7, we'll have the in-person test. Important to note that it won't be in our regular lecture room in ABB. It'll be in T13, which is pretty close to ABB. Okay? So the regular lecture room isn't well suited for testing, so that's why we're moving here. Okay. So test 2 is Tuesday, July 19th. Starts at 7, and it's going to be in T13. Okay. The details of whether you'll be in 125 or another room will be released. And the final exam is on Thursday, August 4th. It'll be a bit longer, and it'll also be in T13. Okay, I'm going to have office hours for this course, and they'll be in Hamilton Hall, okay, at this time, 2 to 5, on these days. Okay, so if you need help with the assignments or help studying for the midterms or any other linear algebra question, you come to the Math Cafe during these times and dates. Okay, so where's the Math Cafe? It's in Hamilton Hall, the Math building. So this is the main entrance here, and the Math Cafe is this area over here. Okay, there's no actual cafe there anymore. It's just tables and chalkboards now. Okay, and these dates are scheduled to be, right when or right before the assignments are due and right before the tests and the exam. Okay. And if you have any sort of questions or concerns, you can always just email me and I'll answer as soon as I can. Okay. And if you'd like to arrange office hours outside these times, I'm open to that as well. Maybe if you want a virtual office hour meeting, just send an email and we'll arrange it. If you have feedback or concerns about the course, then I ask you to please let me know about it, in person or via email. I'm open to adjusting the course based on feedback, and it's better let me know during the course rather than at the end, so that I can make adjustments or help you in some way. Okay, so I'm always open to communication. Okay, so here's a list of topics that we'll be covering in this course. Okay. So Math 2LA3 is a continuation of first year linear algebra. So 1B03 or 1ZC3. Doesn't really matter which one you took. So for the first week or two, we'll review first year linear algebra. Okay, not all of it, just the parts that we need for this course. Okay, from there we'll study orthogonality, some applications of it, look at symmetric and orthogonal matrices, and some applications of that, and sort of the real centerpiece of the course, and what we're sort of building up towards here is the singular value decomposition, which has some very nice applications to statistics and data compression. Okay. At the very end, we'll look at a separate topic, essentially, called linear programming. Okay. So the textbook assigned for this course is Linear Algebra and Its Applications, 6th edition, and that's what the chapter numbers up here refer to, this book. Okay, so I recommend you have access to this book because I'll be assigning some practice problems from it. Okay, but the core content, or the sort of official content of the course, will be what's in the lecture notes. Okay, so there's a lot of stuff in these chapters that we won't use, and there'll be some stuff not in the book that we will use. Okay, so the lecture notes and the assignments are sort of the official stuff for the course, and hopefully those notes will be sufficient and you won't have to look into the textbook too much. Okay. Okay, now we'll talk about what linear algebra is in the context of math, and give some motivating questions for this course. Okay, so what is linear algebra? So, sort of description I'll give is linear algebra is the study of linear functions and matrices, and that'll do for this course. Okay, linear functions are the simplest type of functions. Okay, and linear functions are represented by matrices. Okay, so one of the takeaways from this course is just think about linear functions and matrices as sort of interchangeable. Okay, and in your other courses, say your multivariable calculus course, okay, you study functions, right? But there's really no restriction on the sort of type of functions you're studying, right? So there are, trigonometric functions and exponential functions, logarithmic functions, and so on. Okay, and all of those are complicated, and all of those are not linear. Okay, so in linear algebra, we're still thinking about functions, but we're restricting to linear functions, the simplest type of function. Okay. Okay, so in 2LA3, what we're going to focus on is matrices. Let A be the m by n matrix with real entries. Okay, so you may have talked about complex matrices before, but for applications we want to focus on letting A be a real matrix. Okay, when we say m by n, we mean m many rows and n many columns. Okay, so broadly, our goal is to more deeply understand A. Okay, if we understand this A well, then we'll understand linear functions well. Okay, but of course, what it means to understand A depends on how you think about A. Okay, so I'll give you 3 different perspectives on how to think about what A is, this matrix. Okay, so if we let A be an m by n matrix with real entries, here are 3 ways of thinking about what the matrix A is, or what it represents. The first perspective is the most abstract perspective, called the algebraic perspective. Okay. We view the matrix A as an algebraic object under the operations of matrix addition and matrix multiplication. Okay. So 2 sort of follow-up questions for that perspective is, what is the best way to factor or decompose A? Okay. Another question you could ask is, what are the bases for the associated subspaces of A? Okay. For example, the null space or the column space of A. If you don't remember what those words mean, we'll review all of these. Okay, that's the first perspective. The second perspective is what I'll call the geometric perspective. It's where we think of A as a linear function from Rn to Rm. Okay, where the m and the n come from the rows and the columns, respectively. So, how exactly a matrix induces such a function we'll describe in detail in the first week. Okay. So our question is, how do we describe this transformation sort of geometrically? Okay. How can we geometrically describe how A transforms the space? Okay. So in general, describing how a function does this is very difficult. For linear functions, it turns out there's sort of a limited vocabulary you can use to describe this, or rather, you only need a limited vocabulary to describe it. Okay. Some of the words are stretch, rotation, dilation, reflection. Okay. We'll see that every linear transformation is a sequence of some of those words, essentially. Okay, so the final perspective, and the least abstract perspective, is to view the matrix A as a data set. So a matrix, essentially, is just a box of numbers, right? So if you have some data set of observation from, I don't know, a scientific experiment, and let's say they're stored in a spreadsheet, an Excel spreadsheet, then, right, what you have is a matrix, right? You have rows and columns. So you can think of that as a matrix. And so the natural question is, you know, can these algebraic properties about the matrix tell us anything about, you know, the statistics of the data, or sort of reveal any patterns in the data? Okay. So yeah, that's the final perspective here, which I'll call the sort of data science and statistics perspective. Okay, so in this course, in 2LA, we'll sort of find out that these three perspectives are entangled. And so we'll find a very nice decomposition of A, which will answer all four of these questions for us. Okay, so that decomposition is the singular value decomposition. Okay, shortened to SVD. Okay, that will give us pretty good answers for all four of these questions. Okay, so now we'll talk a bit about what decompositions are. Okay, so in math, a decomposition is a way of rewriting a complicated object, for instance a number, polynomial, or matrix, as the sum or product of simpler objects. Okay, so you've seen decompositions before. I'll give you a few examples. Okay, so decompositions of polynomials. So if we look at this degree 5 polynomial, if we factor it, it can be written as the product of what? 5 degree 1 polynomials. Okay, so we have this complicated degree 5 polynomial, and now we've written it as the product of much simpler polynomials. Okay, and the obvious advantage to that is, right, we can more easily see the roots of this polynomial looking at the factored side, right? So the fundamental theorem of algebra says that we can always do this, right? We can rewrite any degree n polynomial as the product of n degree 1 polynomials, okay, provided we allow complex roots. Okay. So you may or may not have seen it written like this. And there's a sort of similar thing we can do with numbers, okay? Positive integers. Okay? We can do what's called the prime factorization, where we can factor any positive integer into a unique product of primes, right? 8 is 2 times 2 times 2. 250 is 2 times 5 times 5 times 5. And we can do this with any number. Okay. the fundamental theorem of arithmetic says we can do this with any number. Okay. So this breaks any number down to its sort of its most indivisible building blocks, right? And those building blocks are the prime numbers. So another decomposition you've seen is a decomposition for matrices that you saw in first-year linear algebra. Okay? Again, we will review this. Okay? So diagonalization is a way to factor or decompose the matrix, but it only applies for square matrices, n by n, and even then, it only works for a certain subset of square matrices. Okay? So this is the factorization. A equals P, D, P inverse, where P is invertible and D is diagonal. And yeah, this factorization is good and helpful for computing powers of A. And it's helpful for understanding or breaking down the linear function into steps. Again, it's very limited because it only works for special matrices. So what we're going to learn about in 2LA3 is the singular value decomposition, which is sort of the ultimate decomposition for matrices, okay? In a number of ways. Okay? So, first of all, it applies to any m by n matrix. So, any matrix of any size can be decomposed in this nice way. Okay? We're going to assume the rank of the matrix is R. Okay? So R is just a number. Okay? So what we get out of the SVD is two main expressions. Okay? We get an expression that's sort of like diagonalization. We write A equal to U sigma V transpose, where now U and V are orthogonal and sigma is diagonal. Okay? Again, if you don't remember what these words mean, we'll review all of this. Okay? And another expression we get from the SVD is that A can be written as the sum of R many rank 1 matrices. Okay? So suppose A was rank 5, then I can write it as the sum of 5 rank 1 matrices as a consequence of the singular value decomposition. Okay? So what I just said there is very reminiscent of our polynomial factorization, right? Here we had a degree 5 polynomial broken down into degree 1 parts, 5 of them. And similarly, like we're sort of measuring how complicated the polynomial is by its degree here, right? We're going to measure how complicated a matrix is by its rank. Okay, so SVD will give us these two very nice factorizations, or decompositions. Okay. And further from this, SVD will give us answers to these 4 questions we posed earlier. Okay? Okay, so the SVD will give us a way to nicely factor the matrix. It'll also give us a basis for the fundamental subspaces of the matrix A. Additionally, we'll get a way to describe how A transforms the space in a geometric way. And if A is a data set, then the SVD will allow us to compute stuff like the covariance between the variables and the variance, and it'll sort of chop the data up in a way and label which parts are most important to the data in some sense. Okay,